It's the peak of Black Friday traffic, and your monolithic e-commerce application is taking thousands of orders a minute. Suddenly, a single CPU spike in the payment module's database locks up the system threads, and the entire application shatters. Breaking that monolith into microservices resolves this specific scaling bottleneck. However, this shift introduces a new set of challenges: network unreliability and fragmented data. Surviving this distributed environment requires you to handle those new network complexities directly. That demands the adoption of specific, battle-tested design patterns. This map lays out the 5 essential patterns you need: distributed transactions, data management, resilience, communication, and migration. Moving to microservices transfers system complexity from internal application logic to the network communication layer. Traditional ACID transactions guarantee data consistency by tightly locking resources. Stretching those same locks across multiple independent microservice databases creates severe bottlenecks that stall the system's ability to scale. The Saga pattern addresses this by removing distributed locks. It uses a coordinated sequence of local transactions, where each service updates its own database and then triggers the next step in the workflow. This topology illustrates the orchestration approach. A central order orchestrator node acts as the controller, sequentially sending commands to the payment, inventory, and shipping services. If a downstream service like shipping fails, the orchestrator must resolve the partially completed order. Because the earlier local transactions are already committed, they cannot be rolled back in the traditional sense. Instead, the orchestrator issues compensating actions in reverse last-in, first-out order, instructing the inventory and payment services to manually undo their specific steps. An alternative is choreography. This distributes decision-making across the network. Services publish and react to domain events without a central controller, which lowers tight coupling. In distributed systems, network calls must be actively compensated since they cannot be rolled back. Fetching information gets complicated when your data is decentralized across dozens of microservices, as each service operates its own isolated database. We solve this by separating the write operations from the read operations, using CQRS, or Command Query Responsibility Segregation. This lets you optimize and scale the read models independently from the write models. Looking at this split-screen workflow, we combine CQRS with event sourcing. Instead of storing only the current state of an account, the command service persists in a mutable sequence of events, like appending a deposit executed event to a timeline. That event then updates a separate read-optimized view. This setup risks the dual write problem. If a service tries to update its local database and publish an event to a message broker simultaneously, a failure in either step results in broken data consistency. The outbox pattern prevents this. The service updates its database and writes the event record into a local outbox table within the same transaction. A separate process then reliably forwards those saved events to the broker. Reliable systems treat data events as immutable, persistent history rather than passing transient messages. When a downstream service slows down, it forces the calling service to wait. Those waiting connections rapidly exhaust the available thread pools, triggering a domino effect that can cause a system-wide collapse. We apply the circuit breaker pattern to wrap those external calls. It actively monitors the connection and tracks the error rate against a strict, configurable failure threshold. Notice how this logical circuit operates. When failures cross the threshold, the circuit transitions to open. It immediately blocks the network traffic and returns a graceful fallback response, instead of hanging and consuming resources. After a set duration, the circuit shifts to a half-open state. It allows a limited number of requests through to test if the downstream service has recovered, before allowing full traffic to resume. We pair this with the bulkhead pattern, which strictly limits the number of concurrent calls to any single service component. This isolates critical resources so that one slow service cannot drown the rest of the application. Robust microservices assume network failure is inevitable and architect explicitly for graceful degradation. Managing external access across dozens of individual microservices requires a single perimeter entry point to enforce security and routing roles. This illustrates the role of the API gateway. It handles JWT validation, enforces rate limits, and injects a unique correlation ID into every request before routing it to enable end-to-end distributed tracing. Behind that gateway, internal communication should default to asynchronous events. Using an event bus like Apache Kafka lets services publish and consume updates without direct synchronous dependencies. However, asynchronous messaging needs a failure strategy. If a message payload is corrupt or fails processing multiple times, it is routed to a dead letter topic, or DLT. Sending these technically failed payloads to the DLT preserves their exact metadata for a manual human audit. This protects the system from getting stuck in an infinite loop of automatic retries. Decoupling services via gateways and event buses creates an architecture based on strict, decoupled boundaries, rather than a web of direct dependencies. Adopting these patterns doesn't require you to rewrite your entire legacy monolith from scratch. The Strangler Fig pattern provides a framework for executing an incremental, zero-downtime migration. Here is phase 0 of the migration. The API gateway is installed at the perimeter, but 100% of the traffic is still routed directly to the legacy monolithic system. During the transition phase, specific business functionalities, like account creation, are carved out into new independent microservices. The gateway then uses feature toggles to redirect traffic for those specific routes away from the legacy system. Over time, as more services are extracted, the legacy monolith is completely starved of traffic until it can be safely decommissioned. Architectural modernization is an evolutionary process, replacing systems function by function rather than attempting a risky overnight replacement. Microservices transition complexity from the deployment pipeline into the runtime management of data, state, and failures. This topology combines all 5 elements. The API gateway handles perimeter defense. Internal operations use Sagas, CQRS, circuit breakers, and event buses. In Java, this blueprint is executed using Spring Boot, Spring Cloud Gateway, Apache Kafka, and Resilience 4J. You can begin this process today. Identify the most unstable external network call in your current system and wrap it with a circuit breaker. Resilient distributed systems prioritize their capacity to survive an inevitable network failure over the impossible goal of preventing one.